painting should make you happy. It does nothing else. It should make you happy. And if it doesn't make you happy, you're doing the wrong thing. Because it's fun. And if you can do things all of your life that make you happy, needless to say, you're going to be a happy person.
Okay, next up we're going to compute the derivative of this function. The input variable is z this time. We'll be taking the derivative with respect to z. What's the function? It's z cubed tangent of 3z minus sine of 4e to the z. Funky stuff. Before we begin, let's first of all observe that there's two pieces being subtracted. So we're just going to take the derivative of each piece. And here we have z cubed times the tangent of 3z, and that's a product. So we'll be using the product rule there. So let's first write down those steps using that product rule for the first two pieces. It's the derivative of the first times the second plus the first times the derivative of the second. So that was the product rule for z cubed times tangent of 3z. Now next up we're going to take the derivative of minus sine 4e to the z. Let's just use 4e to the z as the inside for the chain rule. Okay, so when we do that, we're just going to be taking the derivative of the outside function sine at first. So we'll have minus cosine of the inside function 4e to the z, and then we have to multiply by the derivative of the inside function. So you'll notice that my colors have disappeared. I'm not explaining as many steps of the chain rule. I hope that it's becoming clearer and clearer with practice. The key is that I take the derivative of the outside function, leave the inside function alone, but then remember to multiply by that inside function. Alright, next up, let's take these derivatives. Z cubed, that seems easy these days. We're doing such complicated functions. When we get to do just a basic old power rule, things are super simple. Okay, moving along. That 3z squared times the tangent's left alone. Z cubed is just itself. Okay, now we need to take the derivative of tangent of 3z. So again, we're going to take the derivative of the outside function, which is tangent here. The derivative of tangent is secant squared. So it's secant squared of the inside function multiplied by the derivative of the inside function, like so. Alright, and then we have minus cosine 4e to the z, and the derivative of 4e to the z, well, the 4 doesn't matter, it's just a constant, and the derivative of e to the z is e to the z, so we can just write it that way. It is its own derivative. Alrighty, we're almost done. We got 3z squared tangent of 3z. And now I'm going to look ahead and kind of plan this out. What's the derivative of 3z? That's just 3, right? That's a linear function. It's just that coefficient 3, the slope of that line. So I see that that derivative is 3. I'm just going to pull it out because I like to put constants, constant coefficients, scalars out front. So we get 3z cubed times secant squared 3z. And then over here, what's going on? Well, we got minus cosine of 4e to the z times 4e to the z. Now I forgot to put my 4 out front. I should have seen that that constant was coming along. So I'm going to do it now. And that looks great. Let's leave the answer that way. That's fantastic.
If you happen to get some of it down in here, who cares? We'll end up turning that into reflections. We don't make mistakes. We have happy accidents. Just don't worry about it. Learn how to use what happens.
Let's solve a different sort of problem. Let's ask the question, where is the tangent line to the graph of this function, cosine of 2x minus 2 cosine of x? Horizontal. Where is it flat? And we'll only consider x values between 0 and pi for simplicity. So first of all, let's remember that horizontal being flat, that's the same thing as the slope being 0, right? So in other words, we're asking where the slope of the tangent line is 0. Well, the derivative measures the slope of the tangent line. So what do we need to do? We need to solve for x in the equation that says that the derivative is 0. If we compute the derivative, set it equal to 0, and then solve for x, we'll figure out exactly where the slope is 0. Okay, so let's compute that derivative. We have to first take the derivative of cosine of 2x. That's the chain rule. The derivative of the outside is minus sine. That's because the derivative of cosine is minus sine. And then we need to remember to multiply by the derivative of the inside, like so. And then over here we're just taking minus 2 times the derivative of cosine. That's because that 2 right here, it plays a different role than this 2. It's on the outside. This 2 is on the inside of the cosine function. That's just a constant along for the ride. So multiplying that minus 2 by the derivative of cosine, which is minus sine, we get that expression. Alrighty, very good. The derivative of 2x, that's just going to be a 2. So I'm going to immediately move that 2 out to the front as a constant after taking that derivative. There's 2 minus signs here. 2 wrongs make a right. So we have plus 2 times sine of x. Great, that's the derivative. But remember, we're not just trying to find the derivative. What we want to do is set that derivative equal to 0 and then solve for x. We want to solve for x right now. So to solve for x, let's move this to the right-hand side. In other words, let's add 2 sine of 2x to both sides of the equation. We get 2 sine of x is equal to 2 sine of 2x. I just moved this piece to the right-hand side. And now we can divide by 2. We get sine of x is equal to sine of 2x. So if we're asking for which x values, is that true? One way to do this is by reasoning about angles on the unit circle. What are we looking for? We're looking for some angle x. Usually we think of an angle as theta or t or something, but x was the variable in the problem. So we're going to call our angle x. And x has the property that if you look at twice the angle x, that would be the angle 2x, right? Then the corresponding points on the unit circle have the same y value, right? The sine is the height of these points, the y value. So we're looking for an angle where doubling it gives you 2 points on the unit circle of the same height, exactly as I've drawn. You can kind of imagine if you make x get smaller, if you move this point a little bit farther down, then twice that point is going to have a larger y value. Right? You can kind of rotate these 2 points around, and they will no longer have the same height. So there's a special sweet spot where this happens, and that's exactly at these points on the unit circle. That's the pi over 3 and 2 pi over 3 angles. That's what these coordinates correspond to. So x will be pi over 3, 2x will be 2 pi over 3. So this works for x equals pi over 3 because the sine of pi over 3, that's that y coordinate, it's root 3 over 2, and that's equal to the sine of 2 pi over 3. It's a special little angle where that works. So that's one solution, that's one such x value, but there's others. Okay, it also works for x equals 0. It's a little bit silly, but if you plug in x equals 0 here, you'll be getting sine of 0 and sine of 0. That's just 0 on either side, if they're equal. And by similar reasoning, it actually works for x equals pi as well. Alright, so let me just write out the confirmations of that fact. Sine of 0 is 0, and that is also sine of 2 times 0. So that satisfies the equation. And then for x equals pi, sine of pi is 0. That's sine of 2 times pi, 2 times that x coordinate. So our final solution is that the x values where the tangent line to the graph of that original function is horizontal are precisely 0, pi over 3, and pi. We can verify that the answers that we just found to this problem are correct using the graph of the function. Here I am on Desmos, and I've graphed the function cosine of 2x minus 2 cosine of x, and we just figured out the x values where the tangent line to the graph of this function is horizontal, where the derivative is 0. We found that those values are at 0, at pi over 3, and at pi. So there you have on the function I've just selected in black exactly the 3 points on the graph where the tangent line is flat, at least for x values in between 0 and pi. And indeed, if you look at those points on the graph, think about a tangent line here, here, and here. The tangent line is horizontal at exactly those 3 points. Okay, now suppose that we hadn't been so clever as to figure out where the derivative was 0 using the unit circle. There's another way we could have proceeded using the graph. So here in blue, I've graphed the derivative of this function. That's what we computed to be the derivative. So the red is the original function, the blue is the derivative function. Looks pretty funky, right? It's nice. So the derivative function, at each point, it's telling us the slope of the tangent line to the original function. If we want to solve for where the derivative is 0, we can just see from the graph that the derivative, the blue function, is 0 exactly at 0, pi over 3, and pi. Those 3 points where the blue function, the derivative, crosses the x-axis, that's where it's 0. Those are its x-intercepts. Those 3 points correspond to where the tangent line to the original function in red is flat, where it's horizontal. So there at 0, horizontal tangent line, here at pi over 3, horizontal tangent line, and here at pi, horizontal tangent line. Very nice.
Hi neighbor, welcome again to this neighborhood. I'd like to show you something. You know what this is? Maybe if I press this button. This is a cassette player with a little cassette in here, and there's nothing written on it, so we'll just have to play it to see what it is. Do you ever imagine things? Are they scary things? Are they scary things? Do you ever imagine things? Things you'd like to have? Did you ever see a cat's eyes in the dark and wonder what they were? Did you ever pretend about things like that before? Did you ever grow anything in the garden of your mind? You can grow ideas in the garden of your mind. It's good to be curious about many things. You can think about things and make believe. All you have to do is think, and they'll grow. Imagine every person that you see is somewhat different from every other person in the world. Some can do some things, some can do others. Did you ever think of the many things you've learned to do? Did you ever grow anything in the garden of your mind? You can grow ideas in the garden of your mind. It's good to be curious about many things. You can think about things and make believe. All you have to do is think, and they'll grow. Did you feel like going like that? Let's give the fish some food. Mr. McFeely, I didn't order any whistles. That's what they call a slide whistle. Did you feel like going like that? There are so many things to learn about in this world, and so many people who can help us learn, and so many people who can help us learn. Did you ever grow anything in the garden of your mind? In the garden of your mind. You can grow ideas in the garden of your mind. In the garden of your mind. It's good to be curious about many things. You can think about things and make believe. All you have to do is think. You can think about things and make believe. All you have to do is think, and they'll grow.